My name is George Ong, and I'm an anesthesiologist based in Sydney, Australia. Thank you, Dr. Pei Po and SSA, for kindly inviting me to give this talk about my work, which sits at the intersection between two topics that I'm super passionate about, TIVA and environmental sustainability. Now, before we start, just some disclosures. So I'm a TIVA enthusiast, and something I always tell my trainees that whenever a consultant is super passionate about a topic, or in my case, a borderline fanatic, always be careful what they preach. So today I'm going to try my absolute best to give an unbiased presentation about why TIVA is the best anesthetic. I'm also the co-founder of Propofol Dreams, a mobile app that assists with TIVA workflow, which I'll talk about today. And everything we do is open source, it's free for the world. And proudly, I have zero financial interests. So without further ado, let me take you on a journey to the land of TIVA and sustainability. And let me share with you our story, how some simple ideas can help change the world. Along this journey, I'll first go through some of the benefits of TIVA, some of the current challenges that exist, and I'll highlight using a real clinical example how we tackled some of these complexities. I'll finish by talking about future directions in our work. So in recent years, there's been an absolute explosion of interest and research in TIVA. And when you seek, you shall find. TIVA has been linked with many clinical benefits in animal studies, observational studies, all bodily systems. So there's many big headlines like Propofol scavenges free radicals, or Propofol suppresses cancer metastasis, Propofol attenuates remifentanil hyperalgesia. There's even a recent study in the BJA which found Propofol might have antiviral effects against coronavirus. However, really only three big outcomes have withstood the test of meta-analyses. So one, a reduction in postoperative nausea vomiting. There's less postoperative cognitive dysfunction and emergence delirium. And three, better quality of recovery scores compared to volatiles. Now, there are a number of big upcoming trials trying to settle this debate of TIVA versus volatile. So Thrive, for example, based in the US, is looking at postoperative recovery profiles, times to extubation, pain, delirium. VAPOR-C by our college, ANSCA, is looking at oncological outcomes. And Vital, conducted in the UK, is looking at 30-day mortality, quality of recovery scores, and awareness. Now, contrasting with all the complexities and confounding in clinical research, basic science research have demonstrated irrefutably that TIVA has environmental benefits. And we're not just talking about like effect size of 30 or 40% reduction in postoperative nausea and vomiting. Here we can see that Jody Sherman's 2012 landmark study found that the carbon footprint of TIVA is 3 to 4 orders of magnitude lower than that of desflurane, and even significantly lower than sevoflurane. So in this case, Prof. Sherman used a life cycle assessment methodology, which accounts for all parts of the workflow. So the production of the Propofol, the syringes, transport, electricity with the pumps, everything was accounted for. So what this really means is that, one or two anesthetists essentially can have the same, using desflurane, can have the same carbon footprint as the entire department. Now, translating from benchtop to the bedside, multiple groups around the world have examined the carbon footprint of TIVA versus volatiles during routine clinical care. So for example, this observational study in BJA 2025 by Bernard examined the carbon footprint associated with 3 anesthesia techniques across 3 teaching hospitals around France. So they compared sevoflurane using end-tidal control versus manually controlled sevoflurane versus TIVA. And they also performed a very comprehensive life cycle assessment looking at the carbon footprints. And what they found was essentially confirmed the earlier studies that TIVA is associated with a carbon footprint about 1/8 to 1/10 that of even low-flow sevoflurane. So, of course, some will argue, yes, it's not all about the carbon. Propofol can indeed have environmental consequences too, such as more water consumption associated with the production of soybeans, or more plastic consumables, which then end up as microplastic in oceans. One of the other big concerns is Propofol is not readily biodegradable in the environment, and it can be toxic to marine life. So what's the deal there? Now, in 2023, Wasp et al. Examined the literature looking at exactly this topic, the environmental toxicity of Propofol. And they quoted one of the worst case scenario estimates of the predicted environmental concentration, the PEC of Propofol, plus its metabolites, In the environment now, it's about 0.15 micrograms per liter. And to put this value in perspective, this is a few thousand-fold lower than the toxicity limit for marine organisms. So it seems like the evidence suggests that the current levels of propofol in the environment is safe. However, we should always get in the good habit of discarding unused propofol into incineration bins and not down the sink or into landfill. So in balance, Propofol TIVA is associated with all these clinical and huge environmental benefits. So why don't we all TIVA? So I think there's a number of barriers to more widespread adoption of TIVA. So as a newer technique, TIVA is associated with a lot of complexities and nuances. Indeed, questions that might rise up like which model should we use? Or, we have to be bothered to enter the patient's age, weight, and height into the pump. And what about awareness when the drip tissues? And now you have to learn to interpret the EEG. So in contrast, we can see that while volatile anesthesia can be a very attractive option, it has been around for longer, there's definitely more familiarity, and the workflow is somewhat simpler. And of course, there's end-tidal monitoring, which essentially makes it a closed loop. So there's less cognitive load in some respects. So the way I like to think of, I guess, human change or changing behavior sort of follows Newton's laws of motion. So first law says that, a person will not change their practice unless there's external or internal force acting on them. Second law says that for any given change, the greater the person's inertia in their old ways, the greater the force required to change. But above all, every decision, every action or inaction has a reaction. And this is Earth's reaction. It's well known that carbon emission is associated with global warming, sea level rising, more extreme weather events. And here's a map of Singapore, overlaid with predicted sea levels using our current best estimates, following our current trends in carbon emission rates. So the area in red are the places below the flood level. And as you can see, even in about 25 years' time, parts of Marine Parade or, East Coast parts may be underwater. By 2100, places like Kelang, Geylang, and Branding Island will become heavily affected. And by 2050, maybe even parts of Changi Airport might be submerged. And Sydney, Australia is no better. More heat waves, more extreme weather events. We're all in this together. Now, I'm not suggesting that switching to TIVA is the magic bullet. We need to keep in mind that volatile anesthetic agents do still contribute to about 3 to 5% of the entire healthcare's carbon footprint. So really, every little bit of change counts. And indeed, there's been a significant recent trend in an increase in TIVA uptake worldwide, especially among the newer generation of anesthesiologists. So for example, in the UK, in the 8 years before NAT5 and NAT7, there's a tripling in TIVA usage. And here's a recent BJ study looking at the Dutch approach to decarbonizing anesthesia. So in the course of 6 years, they managed to reduce their carbon footprint of teaching hospitals by 77%. And this is largely attributed through increased TIVA uptake, eliminating refusing desflurane, and also optimizing their fresh gas flows for volatiles. So in particular, their pragmatic model really resonates with me. So TIVA when possible, volatile when necessary. So far on our journey, we've established that, yes, there's a worldwide trend towards reducing the carbon footprint of anesthesia. Now, whether you share this view or not, the next generation of anesthesiologists, they are going to be more environmentally conscious. They will be embracing and using more TIVA. So our next challenge along this journey is, what can we do to tackle some of the complexities of TIVA? How can we make things TIVA simpler and more attractive? So to motivate this discussion, let me present you this case, a real case for thoughts. So how do you do total intravenous anesthesia for a 60-year-old female with necrotizing fasciitis involving the perineum, needing an urgent debridement? She's 120 kilograms and she's 145 centimeters, which makes her BMI of about 57. So this is a classic challenge for Propofol TCR models, dealing with the extremes of BMI and also age as well. And it's really because all the existing pharmacokinetic models for Propofol are built on non-obese healthy volunteers. For example, some of the questions that pop up immediately are in terms of the practicalities. Which model should we choose? Should we use Marsh or Schneider? But if we use the Schneider model, it doesn't accept these weight parameters. Schneider model doesn't accept females with BMIs greater than about 35. And if we were to use the Marsh model, do we use total body weight or ideal body weight, lean body weight, or some sort of adjusted body weight? And also, what concentration targets should we use if we had a stance? So if we only had a general purpose pharmacokinetic pharmacodynamic model for propofol, well, in 2018, Douglas Eleveld, Stewart's and the team rose up to this challenge. So they pulled together pretty much every single propofol TCI study before that, performed nonlinear mixed effect modeling analysis, and came up with the Eleveld model. So the Eleveld model is a general purpose model. It can be used for anybody from neonates to the elderly and also to the extremes of BMIs. And a number of subsequent validation studies found very good performance throughout the entire patient cohort, with small biases and small errors. However, there are two main problems with the Eleveld model. So one, as you can see from the pharmacokinetic parameters, it's relatively complex to implement. And number two, more importantly, is not readily available in older commercial pumps worldwide. So during one really long, boring free flap surgery, we begin to ponder, now, how can we make this newer general purpose Eleveld model, the one model to rule them all, more accessible to everyone around the world? So when we take it slow and start to break down the problem to the core, so what is a propofol TCI model anyway? Essentially, it's really just a black box. It takes the patient's profiles, age, weight, height, sex, and then converts it into some sort of a variable propofol infusion profile regime. But if you look at it from the patient's perspective, they don't really care about the middle step. The patient doesn't know anything about the rate constants or the volume distribution or any of the differential equations. The patient only sees the only thing that matters in the end is how much propofol is being infused into them. So essentially, only the infusion rate, infusion profile matters. And if that's the case, then what if we could mimic the infusion behavior of the Eleveld model using, say, the Marsh model? So this was our eureka moment. And from this, we want to introduce to you our EleMarsh algorithm, where essentially the fundamental principle revolves around how can we hack the Marsh model so that it behaves as closely as possible to the Eleveld model. So allow me to walk you step by step through how our EleMarsh algorithm works and achieves this. And we're going to use the earlier patient example to go through this. So the first step is we get the patient covariates, their height, their weight, their age, their sex. And then from that, we generate a Eleveld infusion profile as well as the concentration profile. So for example, in this case, we generate the infusion profile for the 60-year-old lady, 120 kilograms, 145 centimeters in Eleveld, and then targeting, say, a effect site concentration of 4. And this is what the effect site versus time concentration will look like. So this will be the gold standard that we want to mimic using the Eleveld model. So the next step is because the Marsh model only has 1 degree of freedom, which is the input weights. So our goal is essentially optimization problem to find the best input weight to use with the Marsh model such that it aligns with the Eleveld model. So let's just start guessing some weights. Let's guess 30 kilograms. So using that weight, what we do is we generate a Marsh infusion profile targeting the same concentration of 4. And then we put that infusion profile into the Eleveld model. So essentially here, the red line is showing what the Eleveld concentration would have been following the Marsh infusion profile of a 30 kilogram patient targeting 4. So I can see here's a big discrepancy between the green line, the gold standard, and the red line. So our input weight guess is probably not very good. There's a big error. Next, we want to quantify exactly how big this error is so we can optimize it. So we calculate the square error. Then we iterate this process of repeating our guesses until the concentration derived from the Marsh infusion profile best match Eleveld. So in this case, you can see the yellow section is the error, which is quite large here. So let's see if we can improve that by improving on the guess of 30 kilograms. So let's say we make a guess of 60 kilograms. So that's what it'll look like. So we're definitely getting closer. Let's calculate the error. So here in yellow, that's the error. So it's small. The square error sum is smaller than before. So it's improving. Let's see if we can improve it further. So try 80 kilograms. So that looks even better. And error is smaller until we reach a guess of 85 kilograms. That is the optimal Marsh input weight, which allows the Marsh model to best mimic the LFL model. So this is so-called the EleMarsh adjusted body weight of 85 kilograms. In practice, it's actually super easy to do this optimization problem. We made it easier using our app called Propofol Dreams to do the entire EleMarsh calculation. So here you can see on the left is a display from our free mobile app, Propofol Dreams. And if you want to follow along the calculations, feel free to scan the QR code to download our app. So here I'll show you how we can use the app to perform this exact process. So here you first enter the patient details down the bottom. So 60-year-old female, 120 kilograms, 145 centimeters. And Propofol Dreams will then calculate the EleMarsh adjusted body weight for you using the optimization algorithm I described before. So the clinician, you will enter this adjusted body weight of 85 kilograms into their Marsh pump. After this, essentially your Marsh model on your pump will now behave identical to Eleveld during the maintenance phase. All right, so the next question is, what effect size target should we aim for? Well, one of the neat things is now that your Marsh is behaving like Eleveld, we can tap into the Eleveld pharmacodynamic component of their model. So this is from the Eleveld's original publication. You can see that it's a plot of BIS values that corresponds to a certain choice of Eleveld effect size targets for a given age based on population averages. And this helps you choose the best target effect size concentration to start with. And we've also built this into Propofol Dreams, as you can see here. So in the case of our patient, with some degree of septic shock, reduced cardiovascular reserve, maybe we'll aim for a BIS of about 49 for general anesthesia. And this will correspond to a effect size target maintenance of 2.5. And as you can see, being calculated here. Now, one of the things to keep in mind with the LFL model is it's an effect site targeting model. And the whole premise of effect site targeting is essentially it wants to get to the effect site target as fast as possible. So the pump has to deliver essentially a plasma overshoot. But the traditional Marsh model is a plasma targeting model. So in order to truly mimic an effect site targeting model with a plasma targeting model, you need to manually deliver that plasma overshoot, that precise plasma overshoot. And this is something that we calculate for you in Propofol Dreams as well. So when you dial up the maintenance effect site target of 2.5, the app calculates here the precise plasma overshoot you need on induction to get there as fast as possible. So in this case, inducing at a plasma target of 6.7. So how you apply this is when you go to your pump, once you, for induction, you set the induction plasma target for Marsh to 6.7. And as you can see, the pump is going to give a bolus of 145 milligrams of Propofol. And this aligns perfectly with what the LFL model would have done. As soon as that bolus is given, and as soon as that plasma overshoot is done, you drop the plasma target to the maintenance value. And from here onwards, your pump, the value displayed on it, will mimic that of Eleveld. And the two infusion regimes will be perfectly aligned. So here is the plot from our case report published, which shows in red the Marsh plasma targets that we use throughout the case, and the Eleveld effect site profile that for an Eleveld pump that would have been produced is shown in green here. And as you can see, what's used or displayed on the Marsh pump mirrors almost perfectly that of what an LFL pump would have done. So in other words, through just a very simple weight adjustment, the EleMarsh algorithm essentially turned the Marsh pump into an LFL pump. And during this case, the state entropy was very stable. We managed to minimize burst suppression, and also there was no arousal phenomena. And the patient had a very timely, clean wake up. So some of you will say, well, that's fantastic. You have an N of 1 example How robust is your EleMarsh algorithm? So to further test this, we simulated 2,768 patients with all combinations of age, weight, BMI between 20 to 90 years old, 40 to 200 kilograms, and that BMI range, both male and female, undergoing what mimicking a real life 4-hour propofol infusion with the TCI effects as targets going up and down. And this is what we found. So here's a plot of time on the x-axis and the effect site concentration on the y-axis. As you can see, our simulated infusion first targets the effect site of 4 for the first hour, dropping it to 2 for the next hour, then back up to 3, and then down to 2. What's shown here in gray is overlay of all 2,768 patients. As you can see, there's minimal deviation between all the gray lines and the black gold standard line, which is what Elevel infusion would have achieved. So in fact, across all the patients and all the time points, the biggest ever deviation in effect site concentration you're going to get when using EleMarsh is only 20%. And the median absolute performance error is only 8% throughout the entire cohort. So in summary, our EleMarsh method has essentially just upgraded every single marsh pump in the world with the Elevel model instantly and free. So with this, we had overwhelmingly positive response from our users, all across Australia, Japan especially, where all they have is the Marsh dip diffuser pump, South American colleagues, and parts of the UK as well. We've also actually, universally unlocked a number of additional benefits when using the EleMarsh algorithm. So one of the characteristics of the Elevel model is that it has a very small KEO, which means that it has a very long time to peak effect, which then translates to large induction boluses. So for users of the Elevel or people familiar with the Elevel model, you know that you've got to be really, really careful with the elderly and patients with shock. So as you recall, the EleMarsh algorithm actually decouples the induction phase and the maintenance phase. So, you're definitely not forced to get to the effects at target as fast as possible. And this actually allows you to perform a more tailored induction. So you might remember from my example, my case, instead of the plasma overshoot of 6.7 that's calculated, I actually opted for a more gentler peak plasma target of about 4. So I wanted to drift to reaching the effects at target a lot slower. And EleMarsh allows you to do this easily. Another thing about decoupling the induction phase and the maintenance phase is it actually neatly solves the challenge of performing a rapid sequence induction using TIVA. Now, rapid sequence induction using a TCI pump has traditionally been a huge challenge. And the crux of the problem is really that pumps can only really infuse at a maximum rate of about 20 to 30 mils per minute, whereas you can push 20 mils of propofol by hand in about 5 or 10 seconds. So how does EleMarsh solve this problem? So shown here is the rapid sequence mode in Propofol Dreams. And as you can see here, because the induction bolus is decoupled from the maintenance phase, when we dial up the maintenance effect site, it calculates the perfect hand bolus here to use for a rapid sequence induction. So you can actually push the manual bolus here, 110 milligrams by hand rapidly, and then this will be accounted for by the pump during the maintenance phase. So, it's a super neat essential solution to the rapid sequence problem. And in fact, a lot of the Elevel pump manufacturers have since started using the same trick as us, decoupling the induction phase from the maintenance phase and starting their own, rapid sequence modes. So where do we go from here? We have so many interesting ideas in the pipeline of Propofol Dreams. We're all aimed at empowering clinicians to improve their TIVA workflow. So let me just give you a few examples of what we're doing. So previous studies have demonstrated that up to about 50% of propofol drawn up is actually just discarded unused, is wasted. In Propofol Dream, we've designed a volume mode, which essentially pre-calculates how much propofol your case is likely to need before you even start it, just by using the patient demographics, estimated duration, and estimated effect size targets. And this way, the clinician can be more informed about how much propofol to draw up, and hopefully reduce wastage. And a lot of the pump manufacturers are actually slowly beginning to integrate this into their pumps as well. So in the EleMarsh algorithm, we also built a wake-up prediction mode where you can estimate the wake-up concentration range based on how deep your patient is during the maintenance phase, based on their state entry values. And later on, we're developing BIS as well as their maintenance plasma target concentrations. This was derived using a sigmoid Emax pharmacodynamic model. And for more details, I refer to you to our 2025 BJ publication. Also, for our American colleagues and other places without TCI pumps, or if your pump ever runs out of battery mid-case, Propofol Dreams also has a very simple infusion table for a range of drugs, propofol, remifentanil, etc., which can help you with that as well. So ultimately, here at Propofol Dreams, we're not just an app. We're a philosophy, we're a belief. We're all about making the TIVA workflow as easy, as safe as possible, and making anesthesia more sustainable. And we believe we achieve this through advocacy. We advocate for our planet, our patients, our fellow clinicians. We engage in education and trying to inspire the next generation and educate them about good TIVA practices. We do this through research. We're constantly dreaming up of new ideas, and we want to share it freely with the world. And we're all about collaborating with everyone around the world who share the same vision, whether you're an engineer, public health physician, anesthesiologist. Ultimately, we all share the same planet, and we do not have planet B. So let's create a future together that we want our children to grow up in, and let's start making those small changes today. So finally, I want to shout out to all my collaborators and fellow Propofol Dreamers here, including Singapore's very own Dr. Celine Tan, who's an insanely talented artist, and she drew this elegant logo for Propofol Dreams. To my collaborators, Dr. Sarah Wong, Dr. Florian Windler from Germany, and especially my co-author, co-founder, Eddie Zhu, who essentially designed all the UI and UX for Propofol Dreams. None of my algorithms could have been useful without his work. Finally, I want to shout out to all of you in the auditorium today. If you share our vision, if you have any ideas or suggestions or comments about TIVA or Propofol Dreams, please reach out to me, send me an email. I love to bounce ideas with you. So for the sake of our planet and patients, let's dream big together. Thank you very much.